really impressed by the way all of this evolved and the very clear ideas that have to be behind the flight control systems and the flight control from the ground and all this leadership. I'm sure you give talks also to many other people who have the need to create leadership in their organizations in all other areas. And I'm sure that would be really useful for them to hear. The next speaker is Stephen Robinson, a very good friend of mine. We met in NASA many years ago. Steve has been astronaut for I don't know exactly how many years. That would be probably 20, something like that. We flew together in Discovery in 1998. I was the only one who had not yet flown in space at that time. And Steve and many other people taught me whatever I needed to know about how to behave in space and all of these things about responsibility and toughness and all these things that Paul has said before. And what is your role when you're up there? Steve flew then later to Hubble, to the space station, and has done many other things that he will tell us. In particular, Steve was outside of the space shuttle in an EVA the first time. The space shuttle flew after the Columbia accident, and there was a lot of things that had to be checked in order for this never to repeat again. And he's going to tell us a little bit about how this went and what were the very special things that were needed to be done in order to return the space shuttle to flight after this horrendous accident. Steve.
Thank you, Pedro. Okay, I will let the experts decide how mission control is going to work today. And if all else fails, we have Paul Nye. I want to thank Paul for that inspiring talk. If you were going to be up in space and risking your life, who would you like to be in charge on the ground? That guy. So it's an honor to be back here in Madrid, and it's great to see Pedro again. Pedro and I have shared many, many experiences, most of which you'll never hear about, I hope, in space. But I think I would like to, at the end of my talk, I hope that the experienced engineers and professors and scientists in the space business at the end of this talk feel that, isn't it impressive what the human race has accomplished? Isn't this great? But I hope that the students here at the end of this talk look at this and think, we could do better than that. Because this is really for you, so I dedicate these talks to the aerospace students here and around the world who own our future. This is the best we could do. You can and should do better than this. So let's talk about what it is. If anybody knows how to turn these lights off, this would be great. And I'll work on my talk. I know Pedro got them turned off one point. I would like these lights here turned off. So what I'm going to talk about here, as opposed to what was in the program, is a little bit about an operational aspect of flying in space. And this really goes back to the question of why not have a completely automatic spacecraft? And of course, we have very many automatic spacecraft in space, and we always will. But the one thing that you can't do in space with computers and robots is you can't repair them if they break unexpectedly. And that's what having humans in space, to some degree, is all about. It's the inventiveness and the way to respond to unplanned situations and the human hands, eyes, and brains backed up by a big team here on the ground. That's what the value of having people up there really is. So once in a while, something happens that you have to fix. So let's talk about it. You remember the shuttle accident, Columbia? We're going to talk about that a little bit in this talk here, and then on the mission that came after Columbia, everything we had to do to recover the space program, sort of from an engineering point of view, from sort of an emotional point of view, and a programmatic point of view, how we had to recover and then fly again in space. Call that the return to flight. We'll talk about inspecting the space shuttle. We'll talk about the big concern about overheating the space shuttle coming down through entry. This will be a rather technical talk. This is a room full of aerospace engineers. I feel very at home with you. We'll talk about decision-making processes in a very large organization when you have very little time to make the decision. Paul talked about his team on the ground. By the ground, I mean in mission control, but also beyond mission control in other parts of NASA, universities, and other countries too. And then, of course, the in-flight crew response, the astronauts' response and preparation for a response to a repair problem, and then finally getting around to actually repairing the problem. So let's talk about return to flight shuttle mission STS-114. Happened in 2005, and by return to flight, this means deciding to fly the shuttle again after having lost the crew and the vehicle of Columbia on STS-107. A little timeline as a reminder, in January 2003, Columbia, the very first space shuttle, launched on an entirely science mission, not to the space station. However, as you all know, a piece of the insulating foam on the external fuel tank of the shuttle came off during the launch. It hit the shuttle, and it hit the shuttle right in the front part of the wing and broke a piece off. This was not known. It was only discovered 2 weeks later when Columbia came back and was lost during the reentry, when the wing actually was destroyed because of a missing piece of insulation on the front of the wing. This was 30 days from the launch of STS-114, which we had been training for about a year and a half at that point. It changed everything. So for the next 2.5 years was a long engineering process of discovering causes. We had a giant government-level study and inquiry into how we could have had this accident. Was it an unknown engineering problem? Was it a human error? It was human lack of understanding of some engineering principles, unbelievably. And then we had to invent and develop new tools to avoid this ever happening again. We had to test all these out and train the people to use them, not just the astronauts, but all the engineers on the ground, and finally go and launch the mission. But let's talk about some of the human factors. Everybody in the space program is a human being, and a lot of things made it very difficult to recover after this accident, because it was an accident we didn't know it was going to happen. So it was on the one hand, it was a shock to lose the people that mattered to us so much, whether we knew them or not. And those of us in the astronaut corps, of course, we knew them very well. But on the other hand, this is dangerous business. So it wasn't entirely shocking. It was something we tried very hard to never make happen. It was very disappointing that in spite of our best efforts, it happened anyway. So first we had to go through the very sad process of finding all the pieces of Columbia to put it back together to find out what happened. But we had our shock, our grief, anger, depression, all the normal emotional problems that you have after something like this happens. We had them each individually, but we had them sort of culturally as a large organization of people who care very much about what we do. This eventually turned into a resolve, sort of a okay, let's go fix the problems, and the best way to honor our lost colleagues is to go fly in space again. This turned into a motivation, almost a competition to try to find the solutions to the problems. Great levels of fatigue because everybody was working very hard. Boundaries between organizations tended to fall away because ideas mattered a lot. Creativity was sort of the key to building the kind of confidence that we needed to go fly in space. And of course, that led in some degree to the very dangerous overconfidence. Aha, we know the problem, now we know the fix. In some cases, that wasn't the case. So, and at the end, we came up with a whole list of new objectives, which I'll show you in just a minute, for the return to flight mission. For the crew, we underwent a huge change. We'd already been training, as I said, for about a year and a half. And by the time we flew, it was 4 years of training. But after the accident, our mission completely changed, obviously, but so did our crew. We added 3 new crew members, so everything changed. We reassigned the task. During that 4 years, there had been a total of 18 different people assigned to this mission. So it was, if you hadn't been on this crew, you were in the minority. We had a lot of repetition. We trained over and over and over. We had 73 underwater runs to train the spacewalks, which are basically all-day affairs. Everything changed as we did experiments to try to understand what was going on. This was plenty of stress with the family, but that's normal in the astronaut business. For the press, of course, we were the only crew in training, or the only crew that was about to fly. So we had a lot of press interest in what we did. Of course, we were fatigued all the time. Everybody watched every single thing we did, and much of it was new, so we had to learn to do it. Plenty of post-accident issues of trying to support the families of the crew members that we lost. And we had 21 official launch dates. So it took a little patience and persistence to go through this process. But our reward was a fantastic series of new things to do in the space shuttle, every single one of which made us safer. The most important was we understood that we could fail. That was the biggest thing that you as engineers hope to never learn the hard way. You try to learn that from somebody else's mistakes, but we had to learn it ourselves. We learned how to fly that insulation better. We learned how to set up cameras both on the ground and radar systems on the ground, and cameras all over the space shuttle itself to watch to see if there were going to be any debris. In other words, foam falling off during launch and damaging the space shuttle so that we would not be surprised again. We pulled together an entire team to look at any kind of damage that we did detect, because we did expect some in the future, and I'll talk about that in a minute. One of the big things was we had a 50-foot robot arm on the shuttle. We developed an extension to the arm that doubled its length so that we could actually look under the shuttle and inspect it while it was in space, something we had never done before. And that carried various kinds of sensors and cameras. We had all kinds of inspection time now put into the mission, and this was part of the cost, because on a mission we used to spend no time inspecting a spacecraft, and now we spent a couple of days of each mission doing it. That was costly. Another thing we did, as we'll see in a picture, is come up and show the belly to the space station astronauts who have cameras before we dock. We had to come up with all kinds of repair technology, because what if we did discover something like what Columbia had, or much smaller, and could we repair it while we were still in space? And all the techniques and tools and robot arm access that we had to support to be able to do that in space. So here's the damage assessment process, and we called it the damage assessment process rather than the damage avoidant process, because we expected to still get some foam falling off at very high relative speeds during the launch process. So on the very first day, as I mentioned, lots of cameras to watch what was going on. On the third day, when we got right up next to the space station, we would flip over, and the astronauts and cosmonauts on the International Space Station would use very high magnification lenses to photograph the thermal protection shield of the space shuttle. And then, as I said, the robot arm with the extension boom would use laser scanners and cameras to look at the tiles. All right, after 4 years, we finally launched. Beautiful launch day. Discovery was back in the air again. This was my third trip on Discovery. So whoops. Don't you hate it when an astronaut says whoops? So, of course, the big thing we learned is to avoid anything hitting the space shuttle. We don't want foam coming off. We don't want anything hitting the space shuttle. So here we go, our first launch after learning that and doing everything we can think of to avoid anything hitting the space shuttle. Look what happens. Whack. All right, I think I do it again. Watch right at the very top of the screen. Watch that big black bird. So we are about 3 seconds into our mission, and we hit a bird about this big. How are we doing so far? I just want to remind you of the space shuttle. It is an accelerating machine. When you get out to the launch pad, it's about the size of a 20-story building, and it seems just impossible that it would ever even leave Earth, but it leaves Earth at a rapid rate. Shows you a couple of things. I think one of the more impressive things is that you go supersonic after 43 seconds. So that 20-story building is going straight up supersonic in less than a minute. After about a minute, you're about as high as an airliner, only you're going twice as fast. And so on. And if you can imagine going almost Mach 8 after 4 minutes after leaving the ground. Now this I can't show because it's a website. But basically what it is, it's one of the many cameras we had on board looking back down towards our wing, showed a huge piece of foam. The insulating foam on the fuel tank came off. Exactly the thing we'd spent 2.5 years trying to avoid. A piece of foam about that big came off, went right down the tank, and didn't hit us. It didn't hit the Space Shuttle Discovery as it had on Space Shuttle Columbia. If it had, well, clearly we would have put all our repair techniques into work, but I'm not sure they would have worked because it would have been a very big damage. So that's the reason we didn't fly another space shuttle for over a year after this. Let's talk about inspecting the space shuttle here on the 114th space shuttle mission. We're finally inspecting it in flight for the very first time. So here's the boom. The robot arm is just up to that corner there, and that 50-foot straight boom with laser sensors and cameras on it. And if you were that camera on the end of that arm and looking at the thermal protection heat tiles on the shuttle, this is what it would look like. So this is the nose of Discovery from the camera on the end of the boom, and we looked at all the tiles and all the front parts of the wing to make sure it was okay. It looked pretty good, but we learned a little bit more by doing this, what we called this rendezvous pitch maneuver, which looked like this. If you were on the space station looking down at Shuttle Discovery arriving, and you've probably all seen these videos, but this was the first time we had ever done it. So it was a very strange thing to do. We were about 200 meters away from the International Space Station and did a complete flip around to allow high definition photographs of the tiles on the bottom of Discovery. Great. It did just what we wanted to do. It gave us all the detail we wanted to see and showed us something we didn't want to see. That little thing, there's actually two of them. You can't see the other one, but we found that two were sticking out. These are little, I'll show you what they are. They're called gap fillers. And if they stick out, they create an aerodynamic threat to the shuttle as it's coming back through the atmosphere. We'll talk about the fluid mechanics of that in just a second. Here's how the tiles work. The green is the aluminum bottom of the space shuttle. The red is a rubberized glue that holds the tile on. In between the tiles, there's these pieces of fairly thin material. It's kind of a ceramic fabric, and it keeps the tiles from banging together during launch because they're made basically of a foam glass, and they would fracture. And that's what was sticking out on the belly. So here's the problem. We asked our team to evaluate. This was something we hadn't seen this far forward on the vehicle before, but on the other hand, we hadn't had the means to see it. So we're probably had happened before, so maybe it's okay. So we asked our team to look at it. We have experimental guys who have wind tunnels and other sorts of tools to look at the re-entry part of surfaces, materials, and the aerodynamics of it. Then we have computational fluid dynamics, very state-of-the-art. It uses not only the Navier-Stokes equation, but the energy equation and real gas effects to compute the thermal environment that the shuttle's going to be going through, and if something was sticking out, what effect might that have? Then we have the flight experiments. This is basically data mining. We look back through the other 113 flights and see what kind of data we have. We don't have as much as we wish we had. because there aren't as many temperature measurement sensors on the bottom of space shuttles as we would like. In fact, the most instrumented one of all was Columbia itself. We asked this giant team, how much should we worry? Well, they kind of reminded us how the thermal protection system works on the bottom of the shuttle, where you have on the order of 25,000 different tiles here. So lots of chances of things to go wrong. We have about 15,000 of those gap fillers. The tiles will protect you up to about 2,000 degrees up the middle here. And then along the leading edge here is 45 of these reinforced carbon-carbon panels, which are good up to about 3,000 degrees. This is one of the things that was broken during the Columbia ascent, and which eventually caused the accident. Now, let's talk fluid mechanics. When a high Mach number vehicle comes through an atmosphere, you get a shock wave. And if you're going fast enough, the mechanical energy of the vehicle coming through the atmosphere is partially dissipated through heat in the shock wave itself. And the more blunt the object is, the further away the shock wave is from the vehicle. It's called a standoff shock. And if the hottest thing in your whole environment is your shock wave, and you don't want to melt, you want to be as far away from the shock wave as you can be. So you want to be blunt. That's why the space shuttle does not come in nose first. It comes in bottom first, like this, the bluntest way we can do it. And that means the shock is pretty far away from the shuttle. The shock is on the order of 5,000 degrees Fahrenheit. The shuttle can only take 2,000 on the belly. So if you get something sharp, if you have some sort of break, some sort of fracture, or something creates something sharp, that's exactly what happened to Columbia. It had a fractured leading edge, and the shock became very close to it, and it simply melted the internal parts of the wing. Now, one more thing on the bottom. Okay, that's the basic idea. On the bottom, when you have flow go over surface, you have a boundary layer, right? And the boundary layer can be laminar or turbulent, depending on the Reynolds number, okay? If you have a turbulent boundary layer, and it's very hot outside the vehicle, the turbulent boundary layer mixes. It's turbulent, so it mixes. So it brings the heat down to the surface, so you don't want that. You want a laminar boundary layer. So the boundary layer serves as an insulator to the surface. The heat stays on the outside. Now, if you have something that sticks out of the bottom and disturbs the surface, it can do two things. It can create turbulence in sort of a V shape right after that disturbance in the V shape. That'll all be turbulent. And the thermal mixing will make the surface behind that protrusion quite a bit hotter. And this shows you that. What happens is, this is what we'll call a roughness. So this is not smooth. If it's perfectly smooth, this will be 0. And this is different space shuttle flights. And this is the Mach number at which the boundary layer on the surface went from laminar to turbulent. And we won't go through the numbers except to see that the blue roughness peaks corresponds to the green Mach number trip peaks. So when you have something sticking out the bottom, it makes the boundary layer go from laminar to turbulent earlier, and you have more heating into the shuttle. So you don't want that. Okay, that sets it up. Let's just look at this one chart. This is time since we enter the atmosphere. And the Mach number decreases. It starts very high, around 25, and goes down around 5 here, I think. This is the surface temperature in the middle of the space shuttle, actually right here on the space shuttle. And here, this blue chart, this blue line is about normal. The surface gets high, it starts to come back down as it slows down, and then naturally the Reynolds number gets high enough because the density is going up, that you get a natural tripping of the boundary layer from laminar to turbulent, so the temperature goes back up for the reasons I just explained. But as you can see, it's not really any higher than it was before because you're already down, you slowed down enough. But let's look at the red line. That's a different shuttle that did have something sticking out about this part. It came in higher to begin with, but that's okay. It's still under 2,000 degrees. But now we got a transition from laminar to turbulent flow on the belly, which heated up the belly to well over 2,000 degrees and actually damaged the tiles because it wasn't on the downside of the curve. So that's what you don't want. And these are other cases of that. So we knew that that had happened before, and we'd gotten very close to trouble. The problem in this case, now here we are back to the STS-114 case. This is discovery. These dots are different little bits of damage or something we had to worry about. These two gap fillers that stuck out are here and here, much earlier on. Remember I said that there would be a V shape of heated surface where it was turbulent. Well, if that V shape started back here, it's no big deal. But if it starts up there, it will give you a very early Mach number transition, which we don't want. So for this one, this gap filler, the V shape would have looked like this. Again, here in this chart, this is time since entering the atmosphere. And the previous red line we just talked about on the upper left corner, this here is this case. This is that's the roughness needed to transition from laminar to turbulent. And that case, that shuttle mission, got a Mach 18 transition. So then that's the worst case ever measured. That was the worst case we'd ever seen. Our case was here. More than twice as bad. We would have had probably about a Mach 23 transition, and no shuttle had ever been subjected to that kind of heating coming in. Okay, so the engineers came to what's called the mission management team, and these are experienced spacecraft and operational engineers, including the flight directors, to make a decision as to what to do. And this is while we were in space. So these two gap fillers are nearly double the previous worst case height. And there's a lot of uncertainty. Nobody's ever seen a case like this before, but it was obvious that there were going to be transition to high heating cases very early. In other words, a very high Mach number. So not only would you have high heat, you'd have high heat for a very long time, giving the tiles plenty of time to get damaged. One other thing is when you stick something out in a flow like that, it's a vortex generator, right? Regardless of all the turbulent stuff. And what does a vortex do? It mixes high to low. It brings high temperature air down to the surface. Another thing we don't want. But in addition to that, it can go right over the edge and get mixed up in the major vortices on the side of the space shuttle. And in one of the cases would have brought that hot vortex right over the leading edge of Space Shuttle Discovery at a temperature that was potentially higher than it could withstand. So we had two kinds of damage. And so the recommendation was figure out a way to do a spacewalk to go get those gap fillers out. Now, when they told us all this on flight, I'd had a background in aerothermodynamics, and I told my commander that I thought that I agreed that I think at least one of them had to come out. One I wasn't so sure, but the other one really had to have happen. But this is a chart directly out of the mission management team that I borrowed. The date was August 1st. The recommendation is come up with this plan. The due date is the same day. So imagine being assigned your homework in the morning and having it due that night. If I were your professor, you would hate me. So to come up with this plan to do the spacewalk, we had to get a spacewalking astronaut to the belly of Discovery with no training, with no planning. And in fact, it had always been told to us as spacewalkers, the one place you know you're never ever going to go near is the belly of the space shuttle. Because the tiles are very delicate, and you are huge. You're not delicate at all. You weigh maybe 600 pounds mass, and you're covered with sharp things, and you could damage the tiles easily. So whatever you do, don't go near those. So they called up and said, hey, guess what? We got to go down to the belly of the space shuttle and do a spacewalk. And so we have to figure out how to get there with the robot arm, which has never been done because we knew we would never go there before, or ever. And this was all done in a matter of days. So folks on the ground jumped into action. We, as I think many of you know, we do most of our spacewalk training underwater. It's not zero G, but you can make most of the equipment be neutrally buoyant. It doesn't sink and it doesn't float. So in that sense, it's a little bit like being in the microgravity environment. And here are gap fillers sticking out all over the place. It wasn't that bad in space, but this person in the spacesuit is trying different tools to get them out. And the trick was, how do I get them out without damaging a sensitive surface? Should never drop your equipment. Of course, they picked the most careful member of the crew to do this. So the first thing they worried about is if they had to saw the material off, that wouldn't they damage those delicate tiles? And we found something pretty interesting, that if you use a saw like this, they don't damage those delicate tiles. It's because the tiles are covered with a glass coating, and that glass coating is so tough that you can't really hurt it. So that surprised everybody. You'd think we would have known that, but nobody had tried anything like this before. What if the tile didn't come out and we did have to saw it then, which we sort of expected to do? We had to make a saw with parts that we had in space, and in your spacesuit glove, very carefully, without holding on to anything, you're attached to the robot arm by your feet, and it's bouncing like this. But you're not allowed to touch the bottom of the space shuttle because it's delicate. So in these very careful, long motions, the plan was to saw off the material. So this is part of the work that was done by engineers and astronauts on the ground who came up with these ideas, tried them out, made videos, and sent these low-quality videos to us in space. This is the very video that we saw in space. So as the crew, as we started to become aware of this whole situation, I think that some of us were excited and others were worried. I know I was on the excited side. But we talked to Mission Control a lot. We talked to the flight director, we talked to the Capcom, and we also got on the radio with the engineers. They sent us lots of things to read. They send us videos. We get their recommendations, but the way it works, just the way Paul described, is they did not order us what to do. They said, here's what we think is the plan. What do you think? And we're hired as engineers too. We had several PhD level engineers on board, and we altered the plan just a little bit. And but in the end, we all agreed on the right thing to do. Did a lot of planning for it, and I was chosen as the guy to go actually do the job. And my biggest worry was that I would get under the belly of the shuttle where nobody had ever been before in space, and that I wouldn't be able to find them. And nobody had thought about this, but me being a worry guy, I thought about this. I thought how embarrassing that would be to do all this work and say, no, I can't find them, sorry. So I made myself a little map. This is the nose of the space shuttle. This is the landing gear door. And here's how the tiles go. And there's where they are. And here's which direction to cut. And all my own little notes that probably only I could understand. And I had those notes with me on my spacesuit. We built a saw out of duct tape and a hacksaw that was on board. And the most important part is this clip to keep it attached to your arm in case you drop it. We had a little holder there where you could see that saw clipped in. I took this picture during the spacewalk. I actually had, this was very fortunate, I had the first digital camera ever taken on a spacewalk, and they allowed me to take it with me on this historic chance because I was going somewhere no one had been before. So here we go. We get in the airlock. My spacewalk partner is Suichi. who is a Japanese astronaut, and we'd trained together for so long, wonderful guy, and he was my safety eyes. We positioned him out on the space station in a place where he could see me because nobody else could. We assumed that we would lose radio contact because we'd never had somebody under the space shuttle before, so they asked me to just keep talking. So just like this, I just gave a lecture about what I was going to do the whole time and kept talking to maintain radio contact so that we would know if we lost it. We went out, got prepared, sent Suichi out on the truss of the space station with a good set of eyeballs and a camera. The robot arm operators were the main people in the whole show. So Wendy Lawrence actually flew the robot arm. She was a Navy helicopter pilot making, I think this was her 4th mission in space. So very, very highly skilled and probably one of the best robot arm pilots that ever flew. So I felt very confident to be in her hands, and then helping her was Jim Kelly, Air Force test pilot, and making his 2nd flight. There's that camera I mentioned. I'm heading out on the arm. It was a great arm ride because to get the robot arm from the space station where they picked me up, attached by my feet, and get me down under the shuttle, they had to put me way out this way. And so for several minutes, I was looking out into space and could see nothing made by human beings for several minutes, not the Earth either. So it was quite an experience. You can see the camera up on my left shoulder there. And the wonderful Canadian-built robot arm, it was great. Both of my parents are Canadian, so it sort of was all came together poetically. So here's a view nobody had seen before, which is the belly of the space shuttle in flight. Coming up close to the tiles, it's the shadow of me. And then Suichi took these pictures from way off on his station. And you can see he had a good view of me just getting ready to pull out that gap filler and getting right down to it. And the whole concern was hitting the top part of the helmet on the bottom of the shuttle. It doesn't look like that would be hard to do because you know where your head is, but when your head is this big, you don't really know where it is. It would be very easy to lean too far in and damage the more tiles. So Suichi was my clearance eyes. But we did all that planning with pliers and saws and all kinds of things, and here's how it went. We started with tool number 1, which is your hand. Found the gap filler, used my little map. Gave it a little tug. It came right out. And there's the glue that didn't hold it on. The second one was larger. This is the one I was really worried about. I considered the first one to be training. This is the one that I told the commander I wasn't coming in unless I had it in my hand. And it came right out. You can go to the Air and Space Museum, the Smithsonian Museum in Washington, D.C., and see that thing right now. There it is. All that effort just for that little thing. I did take advantage of having that camera. I had this spectacular view of the belly of Discovery, which I knew hadn't been seen before, so I wished I had a fisheye lens, and then all of a sudden I realized I was wearing a fisheye lens. You know, my first picture with this camera, it didn't work. And I thought, oh, this is such a... And then I realized I'd left the lens cap on. Just like a tourist. This is what it looked like from my helmet camera, taking pictures of the belly of Discovery. I took 3D pictures. I took stereo pictures of Discovery attached to the International Space Station. So I really had a great place to stand, see a wonderful view. It sure is hard to take pictures with a camera when you're wearing a helmet and you can't really look through. So you just take a lot of pictures and hope for the best. And this is what it looked like. All right, time to go home. Okay, so now we got that fixed. The rest of the inspections look good. We did our mission to the space station. Nobody had been there for 2.5 years. We brought up a lot of needed supplies. We did actually 3 spacewalks. We completely replaced one of the control gyroscopes of the space station, put on a new platform, did lots of work. Time to go home. There is Eileen Collins, the commander of the mission, Jim Kelly, the pilot of the mission. Eileen's an Air Force test pilot on her, I think, 4th mission here. This is not real. There is nobody there to take a picture when the shuttle comes in. But this gives you an idea. Remember, I was talking about coming into blunt end first. For you aerodynamicists, the angle of attack is about 43 degrees. From the bottom, the shuttle glows a lot. This is taken from an aircraft flying in the atmosphere with an infrared look of the shuttle as it came in through reentry heating. But what does it look from the inside of the cockpit? This is absolutely home movies, terrible pictures, and it starts with something you've maybe never seen before, which is a Mach meter on the panel of a spacecraft, and it shows Mach 21. At 222,000 feet, heading north. This is what it looks outside. What it looks like outside. It looks hot. When you look up through the windows over the top of the spacecraft, you see the wake of the shuttle, and you can see a double vortex pattern sort of in the shape of a mushroom there, just very quickly. And you see flashes from a phenomenon known as vortex bursting, which is a pressure-induced vortex instability. We landed back in California, which was a real disappointment because my family is from California, and they had flown all the way to Florida to watch the launch. But the launch scrubbed, and we launched 3 weeks late. So they went back to California and said, oh, we'll come see the landing. So they flew all the way to Florida to see the landing, and we landed in California. So that's the story of why, in some cases, it's very useful to have humans on spacecraft. Thank you. Hopefully, we have a couple minutes for questions. I know we've been running long today. We're excited to be here, so we're trying to say everything we've ever thought of. Any questions? Yes?
What was the purpose for these gap filler protruding the external surface of the shuttle?
What was the purpose?
What was the reason?
Oh, vibrate? Well, okay. Launch, there's a tremendous amount of vibration during launch. I'll show you a little bit of that this afternoon. And it just vibrated out. But the method that they had used to attach them, apparently they had changed a little bit. And it did not hold them in as good as had been done before. So they ended up with gap filler problems that they'd never seen before. So after this mission, of course, they changed it all again. And it never happened again. Yes?
I'm a Stanford guy, too, so I appreciate I saw in your bio that you did your master's there.
Welcome.
Yeah.
Great.
So I was going to ask, I guess, just kind of seeing where a lot of the commercial development is going right now and kind of like the financial situation for NASA.
Yeah.
What would you say is the future of NASA, both from like the administrator, I guess Charlie Bolton's point of view, as well as Obama, and then also what the future of like commercial companies such as SpaceX, Orbital Sciences, and how that's going to develop?
Okay. How much time do I have? The question all is about the future of NASA and how it interplays with the future of other types of commercial spacecraft being designed. Well, let me say one thing about the spaceflight business. By nature, by design, by definition, the world of spacecraft is changing all the time. And if it ever stops changing, in fact, you can make the argument that the shuttle lasted too long. In 30 years, there's a lot of people who don't know how to design a spacecraft anymore. So change is good for the space program, and we're definitely in change. Now the shuttle program is gone. We're still flying the International Space Station. We need to find a way to get to the International Space Station that is made in America, because that's a point of national pride, and it's also an economic driver for people going into engineering in the student population. To do that, we think that we've been flying into, the government has been building spacecraft to fly into low Earth orbit for 50 years now. And it's time to say, you know, we think that technology has matured enough that we can hire somebody else to do it. And here's the good news. There are 6 different human-carrying spacecraft being designed in America today. It's never been the case. I don't think they're all going to fly, but the fact that there are 6 different design teams with different ideas, different engineering cultures, all coming up with different ways to solve this problem using modern techniques more creatively than the government could ever do, and hopefully less cost. That's exciting. Of course, the scary part is safety. That's what we all worry about. And those of us who have been through a major safety problem and have had a major disaster to live with, think about safety differently than those who haven't. That's just human nature. But I don't think there's anyone who isn't excited about all these new ideas coming up with these different companies. Of course, companies, you know, Rockwell built the space shuttle. The government didn't build it. And so it's not really a new concept. So if we can buy our taxi service, which we're doing now with the Russian Soyuz, and we're happy with that, but we would prefer an American-made one, of course. If we can buy our taxi service and then use what NASA does best, which is do stuff nobody's ever done before, then we could start thinking about going out of Earth orbit to some other destination. Our panel session tomorrow is the future of human spaceflight. For those of you who can make it, I really want to hear your ideas. I'll give you my opinions. It won't take long, but this is what we'll talk about. Thanks. I'll take one more question. We'll talk some more later. Any from here? Well, hold on. I want to get any of you folks here? It talks for you. Okay.
Stephen, thank you. Just a question. I wanted to ask you, you know, on a less of a technical front, what was going through your mind and body when you're out there on the spacewalk? What are you thinking? What are you feeling? But less on the technical front.
Well, what you're thinking when you're on a spacewalk is hard to describe, because human experience is transmitted through analogy. I did this, and it was kind of like this. But when you do a spacewalk, it's not like anything else, so it's hard to describe. I think my overwhelming feeling was one of good fortune, of privilege, and trying to take seriously the idea that I'm doing something that many humans would like to do, so I sort of have to be a representative of lots of other people. So it was a big sense of responsibility, which came also down to the sense of don't screw it up. You know, there's many ways to make big mistakes when you're doing a spacewalk. So, was there any student questions?
Thank you.
Yes.
My question is that. Thank you very much. My question is that in case that for these sort of problems that we are going maybe to have in other flights, if we foreseen to design a robot in order to access all of the parts of the outer or inside space of the spacecraft, it cannot, I don't know if it has been thought about, or for example, if we had a robot that could do the work that you have done, it has been thought before, or what is the difference, or?
Yes, we would love to have a robot that could do that. It would be much less risky. What we find, you know, when Paul spoke this morning, one of the things that underlies his job is to try to imagine everything that could go wrong before it does and come up with a plan. And you're not so confident to think that nothing else could go wrong than what you've already thought of. But there's 2 benefits to that. One is you're prepared for a whole lot of different things. And the other is you've taught yourself to think always of things going wrong. So you prepare yourself, you prepare your creativity, your application of engineering principles in ways that you've never done before. You prepare yourself for that kind of thinking because that's what really happens. Okay. Now, if we had a robot that would do that, the robot would either have to be prepared for every possible thing that could go wrong, which we have proven can't be done, or it would have to as flexible and dynamically creative as a human could be. Now, can we say that's impossible? We fly in space. 100 years ago, that was impossible. So I challenge you, as one of the representatives responsible for our future in space, to think, how possible would that be to build that kind of creativity and unplanned response into a robotic system? Okay, thank you very much. We'll talk this afternoon.